All right, welcome to section 5.5, Substitution Rule Part 1. This is first video of a three-part series, and what we're going to be talking about is integrals today, antiderivatives, and the chain rule, and how we anti-differentiate with the chain rule is with this method called substitution. So what we're going to do first is we're going to talk about substitution with indefinite integrals, and then we're going to switch over to examples with definite integrals, which can be tricky. So the two main ideas here are, the idea is to replace a relatively complicated integral by a simpler integral, okay? And the main challenge is to determine the appropriate substitution. So you can use substitution for any integral, but whether it's going to benefit you or not can play a major factor. So that's the big problem, is like, which function do we substitute in for? So we're going to look at several examples. Alright, so our first example here, example 1, is x cubed times the cosine of x to the fourth plus 2, and we're asked to integrate that. So usually what you want to do is I look inside the trig function first, and I know I see that x to the fourth. So I know that if I integrate that, okay, I might be able to get rid of that x cubed. So I'm going to let u be this inside function. So we slide over here, we're going to let u be the inside function, and then you actually take the derivative with respect to u. Okay, u equals x to the fourth plus 2 du dx. Taking the derivative of your function with respect to x is 4x cubed. Cross multiplying, we solve for du and we get 4x cubed dx. I don't see 4x cubed dx. I see x cubed dx. So what I'm going to actually do is solve this equation here for dx. And when I do that, I get du divided by 4x cubed. Okay, so after I solve for dx, I'm going to look back to the function, and wherever I see the dx, I'm going to substitute dx with du over 4x cubed, which is what I've done here. And so by doing that, I'm able to cancel out the x cubes. So I'm just left with du over 4, or 1/4 du. So I bring that 1/4 out, and I leave the du. So the 1/4 comes out front of the integral. So I have 1/4 times the integration of cosine of u du. So now I can take the antiderivative with respect to my variable. Okay? The antiderivative of cosine u is sine of u. So we'll have 1/4 sine of u plus a constant, and we've talked about that in class, because there's multiple functions that would give you this derivative, or this derivative, excuse me. So the constant always has to come along. So we have 1/4 sine. My u, remember, was x to the fourth plus 2, so that gets substituted back in, plus c. Now as we go along, we're going to see a few more complicated functions. So now we're going to integrate square root of 2x plus 1. So you have the square root function, and then you have this function underneath. It's always a good idea when you use substitution that you pick the value underneath the radical. So that's what I'm going to do here. U is going to be 2x plus 1. Again, take the derivative with respect to x, I get 2. Okay, and I solve for du, and I get du is equal to 2 dx. I don't see a 2 dx here. So again, I solve for dx, and I get du over 2. So I'm going to rewrite my integral. I'm going to have the square root of u dx. In the next line here, instead of writing dx, I know what dx is. It's du over 2. So I'm going to substitute du over 2 in for dx. Okay, and I can rewrite the square root of u as u to the 1/2. Okay, and that's what I did here. I rewrote this first, so I said u to the 1/2 of dx, and then I substituted in what I knew for dx to be du over 2. Okay, so now here's what I'm integrating, u to the 1/2 du over 2. Well, I'm going to bring the 1/2 out front like I did in the last example, and then I'm going to have 1/2 times the integral of u to the 1/2 du. And so I simply integrate now, and I get 1/2 times 2/3 u to the 3/2 plus c. Okay? When you do this, you apply the power rule. If we look over here, remember we have to add 1 to the for the exponent, so that's 1/2 plus 2 over 2, which is the 3/2. And you get the same thing in the denominator, 3/2 over 3/2. Well, dividing by 3/2 is the same thing as multiplying by 2/3. And we know that 2/3 times 1/2 gives us 1/3. So we're going to have 1/3 times u. Well, u is 2x plus 1, so 1/3 times 2x plus 1 raised to the 3/2 power plus c. Now in example 3 we get a little more complicated. Instead of having just a square root, we have a square root in the denominator of our function. So we're going to integrate x divided by the square root of 1 minus 4x squared dx. So again, you have to think, well, what am I going to substitute? What am I going to let u be? I could let u be x, but that's not really going to help anything. Like the last example, I'm going to look to the square root, and I'm actually going to pick what's under the square root to be my u value, which is what I've done here. Now I wrote a little bit of different form, du slash dx. Du divided by dx equals negative 8x. The derivative of u with respect to x gives me negative 8x. So du is equal to negative 8x dx. But again, I don't see that. I just have x dx. So I'm going to solve for dx again. And when I do that, I get du over negative 8x. Okay, so let's go from there. We know what dx is equal to. And I look to see my integration, and I have x times u to the negative 1/2. So I brought the square root up. So it's a negative 1/2 power dx. In the next line here, we leave the integral x times u to the negative 1/2, but I've substituted dx now. Dx is du over negative 8x, and that's why I have that here. Now notice our x's cancel out. Okay, so I'm left with du over negative 8, and we're integrating u to the negative 1/2. So I bring that negative 1/8 out front. And now you're starting to see in all three examples how we're bringing some constant out front. So negative 1/8, and we're going to integrate u to the negative 1/2 du. So you add 1 to the exponent, which becomes 1/2, and you have to divide by 1/2. So that negative 1/8 all of a sudden looks like negative 1/4. So let's see how that happened. So you have negative 1/8 times u to the 1/2 divided by 1/2. Dividing something by 1/2 is the same thing as multiplying by 2, and you can see where the 8 and the 2 simplify to be negative 1/4. So there's the negative 1/4. Okay, so negative 1/4 u to the 1/2 power plus c. And now I just have to substitute what my u was. Remember, my u was 1 minus 4x squared, so we have 1 minus 4x squared. Instead of writing 1/2, I wrote that as square root of 1 minus 4x squared plus c. All right, our fourth example is integrating e to the 5x. This one's a little bit easier than the last example, and in this case, we're going to let u be 5x, excuse me. So du dx equals 5. Du equals 5 dx. Again, we don't see 5 dx. So solving for dx, we get du over 5. So I rewrite my integral. Instead of 5x, I write u, because that's what we let u equal. And now I know what dx is here, so in the next line down, instead of writing dx, I write du over 5. That's what dx is. So you can see here, there's nothing to simplify. I can't cancel anything out, but the 1/5 can go out front, and that's what I did. Brought the 1/5 out, and I'm integrating e to the u du. Well, when we integrate e to the x, it's still e to the x. So we're going to have 1/5 e to the u, or 1/5 e to the 5x plus c, and we're done. Our last example with integration by substitution with indefinite integrals happens to be tangent of x. And there's a lot going on here, but it actually leads us to one of our properties. So we have u equals, well, let's start over, I guess. We have the integral of tan x dx. So I rewrote tangent as sine x over cosine x. In this case, I'm letting u be cosine of x. Okay? And when we take the derivative of cosine, du dx, we get negative sine of x. Du is equal to negative sine x dx. Okay? And when I solve for dx, I get du over negative sine of x. So back to the integration. Here's sine of x cosine of x. So I write integrate sine of x over u, because that's what cosine is, dx. And the next line down, I substitute what dx actually is here in red. And so when I do that, the signs actually simplify to be 1. And I'm going to bring that negative sign out front. So really I'm integrating du over u du. Well, actually we don't need that, so we'll fix that. So it's just du over u. Okay? So when you integrate du over u, that's actually natural log. So we have equals negative natural log of the absolute value of u plus c. Negative natural log, we substitute u back in. Our u value was cosine. So we have cosine x here in the absolute value bars plus c. So that's important to remember. Remember when we think about when we differentiated, we looked at the natural log of x, and when you differentiate the natural log of x, you get 1 over x. So to get from 1 over u backwards, it's the natural log. Okay? So that's the last example of substitution with definite or indefinite integrals, and we'll see in the next video to talk about indefinite integrals and substitution. Thanks.